Hi people, I'm going to do a new set of videos for astrophysics. I'm now going to focus on stars. Here it is. So I'm going to be telling you about all of these things here. So classification of the stars, black body radiation, spectral classes, supernova, neutron stars, black holes, all of this stuff. But today I'm actually going just to do an intro. So tell you a little bit about the universe, our sun and constellations. So it's going to be really easy, okay? So that's what we're doing. It's going to be new playlist called Classification of Stars. So it's going to have everything that you need to know about the stars part, okay? So so before I talk about stars, I'm going to tell you a little bit about the universe, okay? So it all started with this thing called the Big Bang. Now, some scientists say it's not actually a bang. It was rapid expansion, so not necessarily an explosion, okay? But what we do know is that happened about 13.7 billion years ago. All matter was infinitely hot and dense in a very tiny point, and it expanded rapidly outwards in all directions, okay? We do not know what triggered, and we do know there was a point in the Big Bang where actually the expansion had to be faster than the speed of light, which we call the inflation time, okay? And this is so it can match the observations that we have at the moment. But as you can see here in the question mark, this is actually something that we are not quite sure. So we know quite a lot about the universe. We know quite a lot actually about the Big Bang, but on the actual point, what happened? What was there before? Why did it happen? There is a lot of things we don't know yet, and physics actually breaks down, so we don't actually can get physics that explains that, or the equations we have at the moment cannot explain that, okay? 10 to the power of minus 43 seconds after the Big Bang, we started to get some particles being created. Quarks, antiquarks, leptons, and photons are examples of those, okay? If you don't know what they are, go on my playlist, my first playlist, which is called Particles and Antiparticles or something like this. And I do have videos about all of these, okay? I'll also put a link on the description as well later on. And then we also had four fundamental forces, the four forces that we know. So gravity, strong and weak nuclear force, and electromagnetism. There is some news that came out recently about a fifth force. I'm not going to talk about it yet because, you know, we need to wait and see what really is happening or not, so I'm not going to mention about this force. But the gravity, strong and weak nuclear force, and electromagnetism, yes, they were created by that time for sure, okay? 10 to the power of minus 4 seconds. This is when we start to get the quarks and antiquarks combining to form protons and neutrons. Again, if you go on the second playlist, the second chapter, I cannot remember the name of the chapter now, but you will see that protons and neutrons are made of quarks and antiquarks, so there we go. Matter and antimatter annihilate, again, is on that first playlist, and they release a large amount of energy, okay? And they created what we now know as the cosmic microwave background radiation. So by that time, this radiation would have a tiny wavelength, not on the microwave region, and the temperature would be 10 to the power of 12 Kelvin, okay? So for you to have an idea, 0 Kelvin is minus 273.15, 0 Kelvin is equal to minus 273.15 degrees, so 10 to the power of 12 Kelvin, okay? The universe was quite hot at that time. Then 100 seconds after the actual Big Bang happened, the protons and the neutrons, they start to fuse and form helium nuclei, okay? And the background radiation was stretched to longer wavelengths. As the universe expanded, the wavelength would be expanded as well, and the temperature decreased. You are going to get to know about Wien's law, where the wavelength of the radiation released and the temperature of that environment, in this case the universe, are related to each other, okay? The bigger the wavelength, the smaller the temperature, okay? Then 377,000 years after the Big Bang, The temperature is now 3000 Kelvin, so this means that the wavelength is even bigger now, okay? The electrons combine with protons and helium nuclei to form hydrogen and helium, which make 98% of the universe, really. Most matter is now neutral, so photons can travel in the universe and they become transparent. 8 billion years after the Big Bang, we have our solar system being formed. And our solar system could form planets like the Earth, where we have an iron core, because we have heavy elements now in the universe, way heavier than hydrogen and helium that we initially had, because as stars are born and as they live, they fuse the hydrogen to helium, helium to carbon, to oxygen, magnesium. So they keep fusing into heavier and heavier elements up to where they reach iron. You're going to learn about this as well. When it reach iron, now they don't release heat. It actually needs heat, so the stars become unstable, and that's when the stars die. If this is a very large star, all these elements that the star formed as it was alive are going to be spread out throughout the universe when the stars explodes, because big stars, they die by exploding into a supernovae, okay? So our solar system had a large disk where we had all these heavy elements, and then we could get planets like ours because of these heavy elements that were formed by the death of earlier stars, okay? And now we are with this cosmic background radiation. Now is on the actual microwave region, so that's quite long wavelengths. This corresponds to a temperature of 3 Kelvin. That's the temperature of the universe, so minus 270 really degrees Celsius, and the universe continues to expand. What happens after? We do not know. It could be that we have a big rip, meaning that the dark energy, which acts like an anti-gravity, is going to carry on, and then it makes that everything expands faster and faster, moves away from each other faster and faster until all matter is ripped apart. We could have the universe to keep expanding, but not faster and faster, and have a very slow and sad death. Or then we could have the big crunch, where the gravity would overcome the dark energy and the universe would collapse under itself. Recent data shows that possibly the second option is the most likely to occur, so that we are going to keep expanding but slowly, and we are going to have a slow death as everything is further away from each other and it just cools down. So it's actually quite dull. So that's on the universe, okay? Now, part of the universe is our sun. This is the life cycle of the sun. We are going to learn all about it, but I'm going to tell you that the sun is expected to live about 10 billion of years. At the moment is about 4.5, so it's middle-life star now. And the sun is a small star, okay? It's actually a tiny star. So it's not going to explode in a supernova. Instead, it's going to expand as a red giant, eject all the gases outwards, making a planetary nebula, and only the core is going to remain, and the core is going to be like the leftovers of the energy of the sun. So because it still shines with light, it's going to be called white, and because it's a tiny star, it's going to be called a white dwarf. Once all the light is gone, it's going to be called a brown or a black dwarf, but we will get there later on, okay? For you to have an idea about the sizes, that's the size of our sun, and comparing, that's the size of other planets, okay? And that's the sun right here. This tiny dot here is the sun, and this is the size of other stars, okay? I actually have a video for you that I'll show you after. This is our solar system again, for you to have an idea of the sizes of things. So here we have all planets up to Jupiter. This is the asteroid belt. It is believed that this was a planet that was destroyed due to the pull of gravity of Jupiter, really. So that now we just have the debris going around. Sometimes, because of something called the Lagrange points, sometimes the planets can interact with the asteroids and set them out of the orbits. They can go towards the Earth or outside, okay? And this is for you to have an idea. So Orbits are quite circular. They are eccentric. They are ellipses, but not very eccentric. Here we go again. Orbits. Pluto is the most eccentric one, but then we have other planets, the trans-Neptunian planets, okay? And Sedna is an example right here, and this is the orbit of Sedna. Look, this is Neptune. This is the orbit of Sedna. And then far, far away, we have the Oort cloud, where all the comets come, okay? So they are here. Sometimes they go in, pass near the sun, and we have the two tails, one tail of the ice melting, the other tail of the ions. And comets are really just dirty balls of ice. They just happen to be moving around. Every so often they pass through us until all the ice is frozen, not frozen, melted really. So comets, they do have a lifetime, and you know, once all the ice is gone, then we stop seeing the comet, okay? Now, really quickly, I'll just tell you, that's the Earth. We are right here in the solar system, which is part of the solar interstellar neighborhood, which is right there. We are inside of the Milky Way galaxy, in one of the arms right there. Someone asked me, and this is, well, we believe that we have a supermassive black hole. Oh, actually, I had someone asking me about the time that Sedna takes to orbit around the sun, and Sedna, so that planet with a very eccentric orbit, is going to be 10,500 years that it takes to go around the sun once, okay? This is us, our local galactic group. We are inside of a Virgo local supercluster, so the big cluster of galaxies. They are a little bit closer together because of gravity. We are inside of a local supercluster. That's still us, and that's the observable universe. So as you can see, we are a really tiny, tiny dot in the whole universe, and we actually, especially in extrasolar planet detection, we are only about this radius long. I mean, we cannot see anything. All the planets that we have discovered so far outside our solar system, they are about here. So we haven't even managed to figure out the whole thing about our galaxy, not only about the observable universe, okay? So here it is. That's all that we know about planets around other suns. Now, stars. I'm going to give you this link. Stars are, by definition, huge balls of gas. They give out large amount of light and heat energy. We are going to learn more about the stars, okay? All this light and energy is because they are so hot that the atoms that make them, they can fuse together. We can have nuclear fusion, and this releases a lot of energy, okay? Our sun, as you could see from the previous slide, is not a big star. People thought it was the biggest and brightest star, but it's not. It's only that it's the closest one together, okay? I do recommend you to see this video just for you to have an idea of the stars that we have and their sizes and how tiny the sun is. And then we have constellations. Now, constellations, they are patterns that stars seem to make from our point of view on Earth. The stars that make up the constellation, they are not even all at the same distances from us. It's just us viewed from our point of sight or our location. They just seem to make and form a pattern. They are not close to each other. They are not bounded to each other. Nothing like this. This is only patterns that we made. And they were quite useful, the constellations, for navigation purposes. So before people knew where to turn, so the very old GPS is really the constellations. So navigators would go on their boats when they were trying to discover Brazil and America and going to, sailing to India. Well, what they were using was really the stars and the constellations. So by looking at those patterns, they would know where they were heading, okay? So they were actually quite important. And again, the stars in the constellations, they are not really close together. They just only seem to be close as we view them from Earth. They are not even at the same distances, okay? I'm also going to put this video here about constellations. It's quite interesting to see what people thought about constellations, and includes why people thought that zodiac constellations were important, okay? And I think that's all. Yeah, I'm going to make another video on more important stuff, really. This is just a you know, an intro. So I'll make another video in a minute. So yep, see you in a bit, and I will be telling you more about stars. Bye. Where do I pause this? Here it is. Bye.